Hi everyone, thank you for joining in virtual presentation for ICRA. My name is Arpan Kusari and I am a research scientist at Ford Motor Company. My talk will focus on predicting optimal value functions based on interpolation of weights of scalarized reward functions in multi-objective reinforcement learning. This research was conducted in collaboration with Professor Jonathan Howe of MIT. In this talk, we focus on the reward function of RL. The reward function is utilized to sample a scalar reward at each state and action. In case of multiple objectives, the easiest and most prevalent method is to combine these objectives through a weighted sum or scalarization. However, the weights are mostly determined by trial and error. Even though it is evident that there should exist a relationship between the weights and the optimal value functions, we have found no prior research supporting it. So how is this helpful to us in the AV business? In autonomous vehicle decision making, nominally we have to optimize three objectives, namely speed, safety, and comfort. For an application such as AV taxis, the passengers might like the car to drive according to their own preference. In the current setup, the decision making cannot be changed without an expensive multi-day training procedure. So we show two novel contributions in this paper. We provide the first theoretically rigorous proof of interpolation through the entire space of reward functions to provide accurate estimates of optimal value function. Also, we show that this theorem can be applied through Gaussian process regression to predict accurate estimates of optimal value functions on three example problems well known in RL literature. In order to perform the interpolation, we need to be certain that the gradient exists. In this paper, we formally prove that given n different objectives, the gradient of the state value function with respect to the set of weights, in this case w and w prime, has to exist and is in fact always bounded by the factored sum of objectives. Given that the rewards at each state and action are finite, we utilize Gaussian process to perform this nonlinear interpolation. We use three example environments with increasing degree of complexity to confirm the approach. The first example we use is of gridworld, a frequently used example in RL. It consists of a discrete grid of states, over here given as 3 by 4 grid, where the agent traverses using the 4 action corresponding to the 4 different directions. There are two terminal rewards, +1 and -1, at the end of the grid, and there is a living reward at each state. We vary the living rewards and the terminal rewards in a nonlinear fashion and determine the difference between the actual and the predicted optimal value functions. We present the results of the grid world in predicting an interpolated living reward. We train living rewards from 0 to -0.5 with a step of -0.1 and predict on the living reward of -0.23. In this figure, part A shows the optimal policy and optimal value function for living reward 0, whereas part B shows the optimal policy and the optimal value function for living reward -0.5. If we see the optimal policies, they are quite a bit between the two extremes. In part C, the optimal value functions for two neighboring points, -0.2 and -0.3, are given which also shows quite a degree of variability. In part D, we get the predicted and the actual values. We can see from those values that they correspond to the second decimal place, which shows the efficacy of our interpolation. So we give the results of gridworld using two different metrics, mean squared error and median sigma, to quantify the difference between the actual and predicted optimal value functions in three cases. We share the results of an interpolation and extrapolation in each case. As previously mentioned, for the living rewards, we vary them from 0 to minus 0.5 by a step size of minus 0.1. In case of an interpolation, the mean squared error is in the order of 10 to the power minus 5, whereas in the case of extrapolation, it's in the order of 10 to the power minus 2, a factor of increase of 10 to the power 3, but even with that, it's within acceptable bounds. For the negative terminal reward, we vary it from minus 1 to minus 5 by a step of minus 0.5. In case of the negative terminal, in case of the interpolation and extrapolation, we see that it's negligible. It's in the order of 10 to the power minus 3 to 10 to the power minus 6. But it depends on the max operator of a value function calculation. So the change in negative terminal reward does not affect the optimal value function on the whole. For the positive terminal reward, we vary it from 1 to 5 by a factor of 0.5. We see that both in the interpolation and extrapolation case, it's in the order of 10 to the power minus 5. To challenge the interpolation algorithm, we next utilize objectworld, which is a version of gridworld with random objects placed with inner and outer colors in the grid. The rewards are then given by a combinatorics of position and outer colors of objects as given in the point 2. We use a 10 by 10 grid with 15 randomly placed objects and 2 colors, red and blue. We vary the positive reward from 0.5 to 1 by a step of 0.1. Here we show the results for reward weight 0.8. The metrics are given in this table between the differences between the actual and the predicted. We see that the mean squared error is in the order of 10 to the power minus 2. In figure A, we see the actual object world setup with the objects placed inside the grid. White represents a positive reward, black represents negative reward, gray represents zero reward. Figure B shows the actual optimal value function, and figure C shows the predicted value function. In the boundaries where the positive and negative rewards lie, that's where the errors in the difference are maximal, but otherwise it tracks the error pretty well. We move on to a continuous state problem, Pendulum, which is well known in the control literature. The objective is for the pendulum to make it upright and keep it upright. There are three combinations, in this case the angle rate, and the action, which gives the reward. We utilize neural network to do the training and evaluation. We change the weight W3 in this case into 3 separate values for training and 0.001 for prediction. We show a box plot in this figure of the value differences between the actual and the predicted. Given that it's a continuous nature of the problem, we see that there is a lot of variability, but we can see that the mean is corresponding to close to 0. In conclusion, we show a direct relationship between the weights of reward function and optimal value function by utilizing Gaussian process. Future work is developing transfer learning of specific behaviors in multi-agent environments. Thank you.